you very much for the introduction. Thanks to Wayne for the invitation and all for the organization and the rest of the organizing team for this excellent workshop. I'm very glad to be here to try to not convince you of doing accelerators, because I think you have been convinced by now. So I'm just going to add my little spice to this conversation, okay? So having thought about all these presentations that have been shown here from yesterday and today, and the discussion we had at dinner, I realized that probably what I'll say is mostly deja vu. So don't be afraid. And I'm not going to put disclaimers as you saw before, because you have seen probably before something like this, okay? This obviously means that there is a lot of tracking on what we are doing, and there is a lot of interest. And even though many of us are doing the same thing, I wouldn't necessarily say that's a bad thing, because that just means that we will still have to see different tastes of different twists of the same or similar solutions that will be coming up and be more solve the problem in a more efficient way of some sort. So to Paul, I would say all has been said before, so then I'm done. And you will be super happy because your schedule will be in place right as you wanted. But since you invited me here, I'll bore you a little bit more, okay? So, motivation. This was, again, what I had to cut, okay? So, CPUs, yes, they have been evolved, and you know, we have seen already today, and I was very happy, the slide that we see on every computer architecture presentation with the gap, okay? So I don't need to show that, okay? Even though this also looks like a gap, you know, you understand this? But what I didn't hear yet, maybe I was distracted doing something else, was about the walls, right? We forgot about the walls. We were always talking about the walls. So here's the wall, okay? So done with this too. No, the wall has fallen, right? And the way to go through it is with the accelerators. And you have been convinced about it. So not going to do anything more in here. But what we have seen is that with these emerging of the accelerator solution, the domain-specific architectures, we see something similar to what we saw in nature that people call this the Cambrian explosion. So there are accelerators popping up every day from many startup companies, from many pieces of industry research and so forth. And many of them are latex architectures, like we saw yesterday in one of these quadrants of the presentation, right? We also do that type of stuff. So, yes. I would like to remind you a quote from Alan Kay that said, well, people who are really serious about their software should make their own hardware. And that's what we are doing today, right? So that's why we see so much hardware. Well, that's fantastic. Obviously, fantastic is for people like us that they get excited when we see companies popping up with different types of crazy hardware that does crazy things. And we see definitely that companies that are mostly on software or doing totally different things like Tesla or Amazon producing their own hardware, not to mention obviously Google and others. But what this makes is a very complicated job for even people that say, I don't want to build a hardware, but I want to use a hardware, what type of hardware I should use. So again, Christina, you showed something very similar to this. This is the result from a European project we were involved in. And one of our tasks was to map on the power performance axes what type of efficiency we could get from different accelerators. And basically, to try to help us discern if you are looking for some low-powered device, what should you pick? And if you are looking for a high performance, what should you pick? And also, due to dinner discussions yesterday, I realized, Christina, that the Formula One car should be in red like a Ferrari, okay? So let's have things correct in place. Now, I will not bore you to death with the results from our papers, even though I will reference some things. So our presentation is mostly high level with the ideas and some insights. So bear with me with that. But I want to start you also with something that you saw yesterday, which is there are many different applications in the field. Okay? And we usually select a domain when we want to do this work on accelerators. And you saw yesterday on Michaela's presentation this nice radar chart with different metrics and how the applications adapt to it. Okay, so I would totally agree with that. And then we are faced with the dilemma of how we should build our accelerator. And I will say there are two main paths that. So one is, like we heard before, is the dedicated path. So you have there 4 different applications and you design an accelerator for each one of them. And I'm showing here the analogy with the tool sets, right? So different tool for a different application. This is pretty cool, right? Obviously, okay, it's super efficient, but in terms of flexibility, not so much. And we do know that these applications in the great machine learning era boom are developing at a speed that is super high and very difficult to ride on. So designing very dedicated accelerators might be great, but probably limited lifespan unless it's inside a product that will live for very long. I'm thinking about cars, but not even that, okay, because I think you can get patches over it. The other path is the generic path. This is the Swiss Army knife approach, right? You put all the tools inside, you can do now everything you want. Fantastic. So this is definitely very flexible, but the trade-off will be not so efficient, okay? There's no free lunch, even though I think we will get the free lunch today. As a very naughty kid, I would say, I want both, okay? I want a high efficiency and I want the flexibility. So who can give me that and how can I do it? I think many of us are trying to do this. So we heard this comment before. Should I go dedicated? Should I go generic? How generic is dedicated? How dedicated is generic? Okay, and I think this is the question I'll try to solve here with the vision that we have. So we have these two ends of the spectrum, the dedicated and the generic, and we can run from dedicated to generic towards midpoint, and from generic to dedicated by adding some extra features to a generic tool, for example, okay? That hammer screwdriver thing is kind of a weird tool, but anyway, maybe some company will start to adopt this at some point. But the real question is what is in the middle, right? In Sweden, we are all about consensus. So what could I put here? So not Swedish, but neighboring country. I have a love for a certain toy that when I was a child, not probably super popular right now, but some of you know. So this is Lego. And I do think that the solution is related to Lego, okay? And by Lego, I mean that we need to be designing Lego blocks that we can assemble them in the way that we feel most proper to solve our problems. Now, this is not easy, right? What I want to say is that this should be a flexible, merging the Legos and building our accelerators will allow us to give us the flexibility, the scalability, the efficiency, and I want them to be working together. And there is a cube on the title, and I'll explain what that is. This was inspired by the new motto of the Olympic Games, faster, higher, stronger. There is a together now. This wasn't in the old times, but there is that. And Lego has been around since 1949, the first piece, I just checked. So they are around for a long time. So what am I talking here about? Everything has been discovered, right? Not in our field, though, right? Okay. So by this time, you probably would like me to tell you how do we design an accelerator. I mean, you know already that we need the Lego blocks. Let's say we have the Lego blocks. What do we do? And now I'll bring you up to a company that you probably know. IKEA, right? So you want an instruction 1, 2, 3, 4, how to build this accelerator. This is to build meatballs. So you can actually download this. Meatballs, very typical Swedish food. No, That's not easy like this. But I can highlight this into three different areas that we have been working on so far, at least. And we concentrate the work on the design, the build, and what I call the run. So I know obviously the goal is the Lego blocks. Keep that in mind. The Lego blocks will be important until the end. And I will concentrate on describing things in the build part because it's what the workshop here is mostly focused on. But just to highlight from the design part, we have some tools to give some very fast, high estimations on how to configure the accelerators, what are the needs and the requirements. We have obviously roofline-based tools also. For the running, we have the resource management and runtime management of the accelerators to try to run them more optimized even after they have been deployed, and managing the scratchpad memories more efficiently. But for the build, we have two pieces of work that I think are quite interesting towards the Lego blocks that I'm trying to show you that we should be building. So, the first work is going from the generic to the dedicated. So I'm lucky I have several PhD students in the team. So I said, okay, one, you start running from this end, from the generic, you start running from the dedicated and start running towards the end. Let's see who wins, right? So picking up the story of the student that is looking from the generic to the dedicated, his path was actually accidentally, we arrived to a very neat solution. Accidentally, I say, even from, I was looking at the examples, I think penicillin and several other scientific discoveries were done by accident. I think rubber was also invented by accident. So the accident in this case is we have been tasked to do a very efficient matrix multiplier hardware, which is basically a systolic array, like everybody probably knows here. And what happened in the meeting of the project was the coordinator raises up and says, I'm sorry, guys, we don't have resources to do your accelerator. So we started scratching our heads, and I asked around, oh, but we have a vector unit that does have all the units I need, right? Right. So what can you do with that? And that was what we did. So we picked up the vector unit resources, okay, that were there available. And in a way, we added up some what I call magic sauce, and we make them look like a systolic array. So therefore, we can have very efficient vector operations and at the same time, with a different personality, very efficient matrix multiplication. And the magic sauce is actually 0.1% of the area according to our estimations. And we actually do have this integrated into the project tape out. Fingers crossed when it comes out for testing, we'll see how this is working. This is an extension of RISC-V. They'll have an extension instruction to support this. So by software, on every instruction, you can decide how these units are going to be used as a vector or as a systolic array. And I think that's pretty flexible. And yeah, some details. This is obviously Gem5, as was mentioned before, as a popular tool. We do use Gem5 to do this. And we run some machine learning simple models. And just to highlight from the results we got, these are different layers of a very simple machine learning. And the one horizontal line says when, so anything below is the vector is better, anything above is the systolic array is better. And you can see this group of layers. The systolic array is much better, the vector unit is much better, and with our solution we can capture both, okay? So that's basically the take I want you to take from this chart. And from these charts, many more here, I just want to show you that, yes, we do the evaluation of it, and obviously we do have minimal area overhead, 3.5x speed up, 70% energy, energy savings in the cache, okay? So, great result by having two personalities. So coming from the generic, adding some sauce, and we can get more out of it. So, but is the work done? Far from being done. So what extensions should we make? How many extensions should we extend the generic, right? Which quality metrics? When we are extending and adding something to the CPU, what are we willing to pay to get out of it? Performance per area could be something. And how should we configure many of these things together? if we have. But most basically, the question that we will have to answer is how dedicated should be a generic engine, okay? And this is the continuing work of the PhD student. I don't have anything to show you at this point in the short future, hopefully. So that was from generic to dedicated. Now, from dedicated to generic, okay, you heard yesterday about Fin. Okay, so Fin can be an inspiration for our starting point, where you have, again, a machine learning model, and you map each, you generate an engine for each layer. Fin does a great job by doing this. We did realize that in certain cases, Fin couldn't get the most out of the resources you were giving. And this is just because when you're trying to do a pipeline aggregation of engines, you notice that you have to match the balance them, and so that you don't get a lot of buffers in between. And this is quite a difficult job. And not always you get an optimal solution for what you have at hand. So long story short, what we're trying to do is get the most out of a data flow set of engines connected together. But then if we cannot make it all, then use a generic engine to do the rest. And that's what we proposed. So we have convolution models. We do have an option A, which is we have a certain engine that can solve all the layers of this model. Fantastic, but not super efficient. Then we have an option like Fin, that we have one engine per layer. And you could think about it. There was a Disney short movie called One Man Band. And it means just that the man is having all these instruments and trying to play. This is what I call a single engine trying to solve everything. Fantastic. You can hear something, but it's not good at anything. Okay. And the option B, I just picked up Angry Birds because there are different birds to hit different targets, right? So that's the idea here. Fantastic. Dedication and generic. But we want both. So what the student did, he analyzed the characteristics of the models, different things happening at different layers, what was happening, and I don't want, again, to go into the details, but the idea is lots of layers in one place, lots of activations in another place. So he designed a methodology that we call split CNN, where we split the CNN into a place, and then we say, up to a point, we have this dedicated engine per layer, and then from then on, I can use a generic engine. And this way, we are optimizing the utilization of the FPGA and getting the most out of what we can do. So this was implemented in HLS, not a great thing in the world, but so super fast to develop, but it was evaluated on an FPGA. Results, yes. Different FPGAs showing the performance for different boards. And again, I'm going just to skip on this. So we have a hybrid accelerator. We call this FIBA, by the way. I think Michaela is not here today. So thank goodness, because Finn doesn't look pretty good on these charts. So I'll go without being blamed here. But the idea I already explained. Finn does a great job, disclaimer, okay? But in certain cases, it cannot find the right balance, and we are able to get through. So we get more throughput. And we get 2x energy efficiency with different models, even compared to, obviously compared to GPUs also. The open questions here are which engines should be made available, which configurations, which combinations of engines make sense. And again, the most crucial question is, how generic should a dedicated engine be? So where will we meet? Okay, no idea. So there was a lot of things about cars yesterday. This was before, disclaimer, this was before I seen the presentations yesterday. So, okay, but no proof there. But if you are aware of the Model T from Ford, you can have it in any color as long as it's black, right? So not much flexibility. And then there is a 3-letter brand, German brand, that is showing off a car that actually changes dynamically color constantly, as I wish, or I feel. Today I feel not so good, so it's black. Tomorrow I feel great, it's white, okay? But in between, what is there? Okay, well, the Lego blocks, remember? And if you go to Gothenburg, you probably, or if you have been there, you know that one of the main car factories is hosted there. And if you go there, you should visit the museum of that car factory, and you will see a real life scale Volvo car in Lego blocks. So it is possible out of small blocks to build a car. Don't ask if it drives. The wheels are rubber, though, okay? But it doesn't drive. Yeah. So, what is the vision? Oh, and by the way, the title there said science fiction, because that's probably what my students call about what I say it's vision. So I say it's vision, they say it's a nightmare and science fiction. Vision. So, I want to build Lego blocks, like I said, and then I want to assemble them inside chips. So one block will be memory, another one will be a CPU, another one will be a GPU, an FPGA, a vector unit like the one we built, for example, a depth-wise or a point-wise dedicated engine, obviously sparse support, and X and Y, which we still don't have any idea what they are. And people from industry are probably now shutting off because saying this is totally confusing and nightmarish, so don't do it ever. And I totally agree. And I go and remind you again, we are on the latex building chip part. So we are here just to pitch ideas. So some of these things probably can be catch up at some point. But yes, this is a really probably a nightmare to do software for these things. And computer architects are great at building nightmarish architectures for the software. We are trying now to have co-design so that we solve all these things. So, but depending on the target, you could have different of these chips built with different Lego pieces. And that's the idea, right? And so I want different Lego pieces to be working together. And I also want processing in memory and near memory processing and all this. So the first together is the different Lego pieces working together in a single chip. But then I want to make this more complicated than having tiles of these things. So now that I have tiles of these things, I want them, the tiles also can be grouped together to work. And this is the together squared. So now we group the tiles together and we can get a solution for our problem. So tiles working together. And finally, since there are so many resources available there, maybe what I need is a super engine with 4 times the amount of memory. Okay, so just disable some of the Lego blocks on the nearby engines and use all the memory for the thing you need, because on-chip memory access is much more important than going outside. So use the resources together, okay? And that's the together with the cube. So that's the idea of the together. Obviously, we do other things too, but that was the main vision. We also accelerate, and this is automotive, so self-driving car systems are, if regular ML and LLMs are all complex, for self-driving, it's even worse. So now we have many models doing many things at the same time. Then we combine the models, then the accelerator for this is totally crazy. But the idea of this project is to work on processing in memory and near memory and in-memory processing, working combined, something similar to what we saw in the presentation before. So fantastic segue to us. Also quantum computing, and again, I'm quantum computing almost illiterate. So don't ask me the quantum stuff, that's for the physicists. But we want to accelerate. But what do we want to accelerate? We don't accelerate quantum computing, okay, let's make this clear. They are the accelerators of everything, so that's it. But one of the major challenges with quantum computing today is that we don't have big enough quantum computers to solve the problems we want. So we need simulators, and simulating a quantum computer will never be good enough because, as we know, classical can never match the quantum. So we are breaking them down to different levels, but still huge amount of memory and compute requirements in order to do simulations for that. And we are trying to accelerate those. That's one of the things. The other things that we are trying to look at is how to accelerate error correction for quantum computers, which is a very challenging problem. And we need there to do the error correction before the qubit dies. Basically, that's one of the problems that needs to be solved today. Okay. Again, not more on this. So to conclude, lots of applications. We want to design an accelerator instead of doing a monolithic accelerator or a dedicated accelerator, I think we should go and build Lego blocks. We have done the FIBA, which is a hybrid accelerator, data flow, and single engine. We have done a unit to couple to a processor that helps GEM operations work in a vector unit resource space. And this allows us to save on resources. We have tools to estimate these things and how to configure and the runtime. And the vision is to go through a very complicated tile base with multiple Lego pieces to allow us to be growing to the future with a flexible, scalable, and efficient together architecture. And before I complete, I just want to thank our obviously sponsors from the European projects and local research projects and PhD and postdoc students involved in all the work that I've said here. I just do the funny drawings and the funny pictures. So thank you very much.
Thanks for a great talk. Any questions from audience? Okay, let me ask one question. So in the talk, you mentioned two topics. One is from generic to dedicated. Another one is dedicated generic. So, but most of the presentation focused on architecture level. So my question is, have you thought about, like, after exploring these two topics, like what the compiler or software support should look like? And especially, in the end, you have the Lego building block. So in the end, so I guess when you have a lot of heterogeneous processing engines in your system, that will add a lot of complexity in your compiler, your mapping, scheduling, and software support. So just what is your thought about the compilers?
Yeah, so that's a great question because it all boils down to that. I mean, we have seen in the past several great architecture processors and accelerators that couldn't survive for long because there were not enough tools, especially compilers, to exploit the potential that the architectures have. So the approach we took was, let's start, I mean, we are not in the middle yet, but let's start exploring these things. Let's see if there is any potential at the architecture level that we can exploit. Doing by hand a lot of things at this point. And now actually the main work, so the student that developed this hybrid accelerator FPGA with the engine is actually doing a compiler for this. Having in mind also that it's not just towards what we do. I mean, what his realization is that every day there is a new module, a new engine, a new accelerator popping up. And we should have tools that are flexible enough and modular that you express only at the level of the interface, for example, of a certain block. And then you say, okay, but now if I have all this available to me, how should I bring them together? How do I match them, given the resources? And then most important, given the metrics that you want to achieve. You want to minimize for cost, you want to minimize for energy, you want to minimize for cost and energy. So all this, but definitely the effort now is actually, so this was mostly architecture for this presentation, but the effort now is growing to the compiler level for sure.
Thank you. Thank you. Thank you again for a great presentation.
Thank you.